Hi and welcome to the first of 3 videos from the mechanics course. That's a year 2 content, and so what we're going to be having a look in this first video is those top 2 bullet points there, which is looking at the forces that are acting on a projectile during its flight, and then secondly how we deal with projectiles generally, which is by splitting it into horizontal and vertical components. So here we go. First of all, let's just do a bit of an intro and let's just have a think what's happening if we've got a projectile in flight. So we've got this example here where we've got a girl and she's going to kick a ball off the top of the cliff there, and boom, there it goes. And so now, as it's falling, what forces are acting on it? Well, clearly we've got air resistance that might be acting horizontally or vertically. But of course, in this model, as in all models, our object, in this case the football, is being modelled as a particle, so therefore we're assuming no air resistance, so we can get rid of those forces. The next one is gravity. Well, clearly there's definitely gravity acting on the ball. That's what's making it fall to the ground. And other than that, that's basically it. So what we've got is just the one force acting on this ball. As soon as it's left the girl's foot, the only force acting on it is gravity. And the biggest impact of that is particularly for its travel in the horizontal direction. Because in the horizontal direction, since we've got no other forces acting, then Newton's first law applies, and clearly you can all remember your Newton's first law from last year. If you can't, there it is. Every object remains in a state of rest or uniform motion in a straight line unless forces act on it to change that state. And the key thing here is this bit here, the uniform motion. So essentially the velocity at which it leaves the girl's foot is going to be constant throughout this entire motion, which basically means in our particular model, if the ball wasn't being acted on by gravity and didn't hit the ground, it would just keep going in the horizontal direction forever and ever at a constant speed. Now, clearly, we know there's an issue with that one because we've got air resistance and so on, so in reality there are other forces acting on it, but in our initial model, these trimmed down models where we're not taking into account air resistance, it means essentially what we've got is a horizontal velocity that is constant. Okay, that's a key idea that we're going to be using throughout this entire section. Now, because we are looking at forces acting on it, because we've talked about horizontal and vertical forces, that's essentially how we're going to treat everything from here on in. So we're going to separate the whole thing out into what's happening horizontally and what is happening vertically. So, there's our girl again. She's going to give the ball a good old kick, and what we've got is the path that it takes is a parabola, and you'll see where that's coming from in a minute. And it's going to be defined by, well, the initial kick is going to be defined by a speed, which we're going to call, an initial velocity, which is u meters per second, and at a particular given angle. And if we've got our initial velocity, which is u, and we've got the angle, that means the horizontal direction, the horizontal component of that velocity is going to be u cos theta, and that's an idea hopefully that we're pretty familiar with now. And the initial vertical velocity is going to be u sine theta. And you'll notice that I've just gone u subscript x to indicate my initial velocity in the horizontal direction, u subscript y for my velocity in the vertical direction. Now, since we've got constant forces acting in both directions, in the horizontal direction there's no forces, so we've got a equals 0. In the vertical direction we've just got the one force, which is due to gravity. What that means is acceleration is constant. So all of these calculations we can use using our SUVAT equations. So let's just have a little look at what's going on. In the horizontal direction, there's v equals u plus at, all in the horizontal direction, hence the subscript x's. And clearly, if a equals 0, that leaves us with velocity at any point during the motion is always going to be the same as the initial velocity. In addition to that, what we've got is s equals ut plus half at squared. And again, with acceleration being 0, that leaves us with s equals ut, and we already said that u was the same as v, so we've got our distance travelled is quite literally just velocity times by time. So that's the horizontal direction. What's going on vertically? Well, in the vertical direction we've got our acceleration is just going to be minus g. We're going to model upwards has been positive direction and downwards has been the negative direction. So acceleration is minus g, so our v equals u plus at simply looks like that. And our s equals ut plus half at squared simply looks like that one there. But for me, I just go back to, I don't tend to remember these kind of new, slightly changed versions. I would just go back to our initial versions here and then just plug in
essentially in this case it's the g, and that's the change sign, but they just plug those in as being minus g, and away we go from there. Now the last thing to note is I said at the top of the slide that the path that the ball takes is a quadratic, and clearly you can see down here, there you go, there's your quadratic just in terms of t. So that the vertical height, or the height above the ground, if we plotted that, would be the vertical height sy against t being our other variable, and like I say, we're going to get a quadratic curve because it's in terms of t squared. Right, that's all of that, the basics and intros all done and sorted. Let's now have a look at how we go about solving problems with this. So here we go. We've got a batsman hitting a cricket ball at an initial speed of 20 metres per second and at an angle of 55 degrees above the horizontal, and we've got a bunch of questions that we've got to solve here. So let's deal with these things one at a time. So first of all, we've got to find the horizontal and vertical displacements when t equals 3. So after 3 seconds, essentially saying, well, where is this ball? So here we go then, horizontally. Well, let's just have a little look at what's going on diagram-wise. There we go. Always like little diagrams to help with my thinking. And there's all the SUVAT stuff in the horizontal direction. So S, that's the thing we're trying to find out. U, that's our 20 cos 55. V is the same as UX. A is 0. T equals 3. Now, to be fair, based on what I said in the previous slide, we don't really need all of that, because the more you get used to it, you'll realise that it's just a case of essentially doing that. So Sx equals Vx times by t, velocity times time. So all we've got to do here to find S is do velocity, which is 20 cos 55, times that by 3, and we end up with 34 metres. So it's travelled 34 metres in the horizontal direction. What's happening in the vertical direction? So let's go for it again. So here's all the bits and pieces we need. This time our u is 20 sine 55. Now, in the vertical direction, because we've got acceleration, which is minus g, the vertical velocity is always going to be changing. We don't know it at this point in time, so we don't know that one, so I'll put across there. There's our minus g for acceleration, and t equals 3. So this one we have got to work through. So we're going to go for s equals ut plus half at squared. Plug in the values that we've got, g being obviously 9.8. And there you go. There's our answer. So after 3 seconds, this ball has travelled 34 metres horizontally and is 5 metres off the ground. And I'm assuming that this will have happened. Let's say if we have a look at our diagram, the ball's come up and it's currently, I suspect, it'll be on its way down and 5 metres off the ground. Right, that's part A sorted. Let's have a look at part B. So there's our diagram. Now, we're being asked for the speed and the direction. So speed is the magnitude of velocity. Therefore, we need the horizontal and vertical velocities. And so there's all the SUVAT stuff that we've got in the horizontal direction, and but we just know that our velocity in the horizontal direction is just fixed. So straight away, 20 cos 55. So that's 11.4 meters per second. Moving on to our vertical velocities, off we go again with the information that we've got, and we've got v equals u plus at. Plug in the values, 20 sine 55 minus g times 3, and we've got minus 13.01. So that kind of bears out what I said previously about, I suspect the ball was on its way back down. So it's, the vertical velocity is negative because it's travelling downwards after 3 seconds. Now we've got to finish off because we need speed, so therefore we're going to need a bit of Pythagoras initially. So there we go, there's our speed, 11 squared plus 13.01 squared. Doesn't matter about the minus in this case because speed doesn't have direction. So there we go. So there's our speed, 17.3 meters per second. And to get our angle of travel, we're just going to need a little bit of trig. So let's pop that in. So alpha is 10 to the minus 1 of 13.01 over 11.47. So we've got 48.6 degrees. But also we need to include the fact that that angle is below the horizontal, because obviously it could have been travelling upwards. In this case it's not. It's travelling downwards, so it's 48.6 below the horizontal. Right, that's part B done. Moving ever so swiftly on, we've got the length of time the ball is in the air. Okay, so when the ball hits the ground, we know a certain fact, and the fact that we've got is this one. The fact that the vertical displacement is 0. So what we can do now is just plug that into the relevant equation. There it is. And so let's stick 0 equal to u, 20 sine 55 times t minus half gt squared. That gives us a quadratic which we can solve in terms of t, which is what we're after. So there we go. So what I've done is take the 20 sine 55, that's the 16.38. And now we're going to get two values from there. The first one when t equals 0, and that's the point at which the ball has been initially hit, and the one that we're interested in, which is t equals 3.34 seconds, and that's when it hits the ground again. Right, there's the length of time it's in the air. That's that bit done. Let's go on. Now we want the maximum height reached by the balls. Now there's a couple of ways we can go about this one. The way I'm going to do it initially is to consider the maximum height when the ball stops going up and starts coming back down. So what do we know at that particular point? Well, that is when the vertical velocity is instantaneously 0. And again, that's an idea that you'll have seen in year 1. So what that means is we can put that value into our v equals u plus at. There we go. And solve that for t, and we get t equals 1.67 seconds. Now, key idea to note here is that we could have figured that out from the value we had over here, but because this, I mentioned it's a quadratic, it's a parabola, it's therefore symmetrical, so what goes up must come down, and it does it in the same way. So we could have just gone, okay, well, the highest point that it reaches is always going to be half the total, the point that's half the total time of travel of the particle in the air. So that's just due to the symmetry properties of the quadratic. But we've kind of just proved it there anyway. So now we know that the maximum height is reached at the point when time is 1.67 seconds, but we're being asked for what the actual maximum height is. So now what we've got to do is take our 1.67 and plug it back into this one here. And there we go. And so that gives us the maximum height the ball was reached is 13.7 meters. Okay, so the purpose of that example was just to go through kind of the basics, the ideas, the key features about the fact that when kind of vertical velocity is 0, or when the particle hits the ground again, we've got vertical displacement is 0, and just get our heads around this idea of being able to split it out into two completely separate bits, vertical and horizontal components. Let's now move on and have a look at something that's got a few more bits and pieces in it just to make life a little bit more tricky, something more similar to what you might get in the exam. So what we've got here, particles projected with a speed of 25 meters from a point that's 10 meters above the ground, and we're given some information about the highest point, which is at B, which is 8 meters above the point of projection, and we've got a whole bunch of questions we've got to solve. So here we go. First up, the value of theta. So the thing we know that our maximum height is reached when Vy equals 0. We saw that previously. And so if we have a look at all of the bits and pieces relating to that, we know that that thing is going to be 8. We've got Uy is 25 sine theta, and it's the theta that we're trying to find. We've got our acceleration is minus g, and t is the thing we don't know at this particular time. So we'll go with the information we've got there, and the equation we're going to need to use then is going to be v squared equals u squared plus 2as. Put all our information into that, and we're going to end up with an equation that just in terms of theta, so it's now a case of solving that equation. So we end up with sine squared theta is 784 over 3125, and then so that gives me the square roots, and then sine to the minus 1, we end up with theta being just a little bit over 30 degrees. Okay, that's not too bad at all. So now we've got theta being 30 degrees, the distance AC, so we need that distance that's just appeared on the diagram there. Bit of Pythagoras is going to do it for us here. We know that AO already is 10 meters, so we've got that. In this particular case, I've said, well, kind of SY is minus 10 because we are 10 meters below our starting point. But when we do the Pythagoras bit, that's not going to make a massive difference. We just need to find the horizontal distance. In order to do this, we're going to find the time at which the particle hits the ground, and this is where this piece of information becomes useful, because what I'm going to do is use that to find the value for t with all the information that I've got in terms of the vertical distances, or the vertical components. Stick it into s equals ut plus half at squared, with that value of minus 10 being our vertical displacement. There we go. And we've ended up with a quadratic in terms of t, which we can now solve, and we get t equals 3.19. Now, once we've got t equals 3.19, we can now go back to our horizontal equation, and as we know, because acceleration is 0, we don't have to worry about that bit. And because we've already got theta, cos theta, we've got theta is 30 degrees, so we've got everything we need, plug it all in, and there you go, there's our horizontal distance, or our horizontal displacement. Now if we want the distance from A to C, again, in this case it's just going to be a bit of Pythagoras, and so we end up with our distance being 69.8 metres. Okay, and so on we go to the final part of the question, which is the speed at which the particle hits the ground. So we know it's hitting the ground when t equals 3.19. So let's find our velocities at that point. So our horizontal velocity, again that's one that doesn't change, is just going to be the same as the initial velocity, 25 cos theta, which is 21.6 because we know the value of theta. And for our vertical velocity, we've got 25 sine theta minus 9.8 times 3.19, which is minus 18.7. And then just all we've got to do now is finish off a speed, bit of Pythagoras, and there we go, 28.6 meters per second. And there we go. So there's the basic intro to your projectile stuff. We've got another couple of bits to come later on, another couple of videos, but we'll deal with those later on. Right, cheers.